Have you ever wondered why organic chemistry is so pivotal to our daily lives? Well, sit back and join us as we embark on a journey to the dawn of organic chemistry. This intriguing branch of science, dedicated to the study of the structure, properties, composition, reactions, and synthesis of organic compounds, has a history as fascinating as the molecules it investigates. Our story commences in a time when scientists believed in the concept of vitalism. This school of thought proposed that living organisms were fundamentally different from non-living entities because they contained a vital force. This force, unique to life, was thought to be responsible for the creation of organic substances. But this belief was about to be challenged. Enter Friedrich Wöhler, a pioneering chemist from the early 19th century. In a moment of scientific serendipity, Wöhler synthesized urea, a common organic compound found in the urine of mammals, from inorganic starting materials. This was a revolutionary accomplishment, as it was the first time an organic compound was created without the involvement of a living organism. Wöhler's experiment, conducted in 1828, marked a significant turning point in the history of science. It debunked the theory of vitalism, proving that organic compounds could be synthesized in the lab from inorganic substances, thus discrediting the notion of a vital force unique to living organisms. From this groundbreaking moment, the field of organic chemistry began to take shape. Wöhler's synthesis of urea served as a catalyst for further exploration into the mysterious world of organic compounds. This was the birth of organic chemistry, a field destined to reshape our understanding of the natural world. The mid-19th century ushered in a new era with the emergence of structural theory. As scientific thought advanced, the mysteries of organic compounds began to unravel. A significant breakthrough came from the minds of two brilliant chemists, August Kekule and Archibald Scott Cooper. Their work illuminated the structure of benzene, a critical organic compound. Kekule, a German chemist, was drawn to the enigma of benzene's structure. Legend tells us that he dreamt of a snake biting its own tail, a vision that inspired him to propose benzene's circular structure in 1865. He suggested that 6 carbon atoms create a ring, with 1 hydrogen atom attached to each carbon. Meanwhile, across the English Channel, Scottish chemist Archibald Scott Cooper independently arrived at a similar conclusion. Cooper, who was a strong advocate for the use of diagrams in chemistry, proposed the same cyclic structure for benzene. He went a step further, indicating the alternating single and double bonds in the ring, a concept that was revolutionary at the time. These discoveries were not just about benzene, they represented a significant shift in the understanding of organic compounds. The elucidation of the benzene ring structure provided a foundational basis for understanding the structure of countless other organic compounds. This was the birth of structural theory, which fundamentally changed the way chemists viewed organic compounds. Rather than seeing them as mere collections of atoms, they could now visualize these molecules in terms of their three-dimensional structure, their bonds, and their spatial arrangement. This breakthrough in structural theory gave chemists a new language to describe organic compounds. It allowed them to predict how these compounds would behave in reactions and how they could manipulate these structures to create new molecules. And so, the foundation was laid for a deeper comprehension of organic compounds and their intricate structures. This understanding would guide countless discoveries and innovations in the centuries to follow, forever changing the landscape of organic chemistry. The late 19th and early 20th centuries brought revolutionary breakthroughs in organic chemistry. Let's dive into the Grignard reaction first. This was a monumental achievement by French chemist François-Auguste Victor Grignard. His creation of the Grignard reagent, a carbon-based compound with a particularly reactive magnesium atom, was a game-changer. This reagent had a knack for forming new carbon-carbon bonds, a critical process in the synthesis of a vast array of organic compounds. For his work, Grignard was awarded the Nobel Prize in Chemistry in 1912. But organic chemistry wasn't just about creating new compounds. It was also about understanding their structure and behavior. Enter spectroscopic techniques, specifically nuclear magnetic resonance or NMR and infrared or IR spectroscopy. These techniques gave chemists the ability to peek into the inner structure of molecules, revealing the arrangement of atoms and the types of bonds between them. It was like handing a map to a traveler in an unknown land. Then came the Woodward-Hoffmann rules, named after Robert Burns Woodward and Roald Hoffmann. These rules provided a crucial understanding of how organic reactions occur, specifically the stereochemistry of these reactions. They explained how the three-dimensional arrangement of atoms in a molecule can influence the course of a reaction. This was a significant step forward, as it allowed chemists to predict the outcomes of organic reactions with a high degree of accuracy. Lastly, we have E.J. Corey's concept of retrosynthetic analysis. In simple terms, this is the process of deconstructing complex organic molecules into simpler ones. It's a bit like solving a complex puzzle by breaking it down into smaller, more manageable pieces. This approach revolutionized the way chemists think about organic synthesis, making the process more logical and efficient. These advancements transformed the way we analyze and synthesize organic compounds. From the Grignard reaction to retrosynthetic analysis, these breakthroughs propelled organic chemistry into a new era, laying the groundwork for the exciting discoveries and innovations that were yet to come. The field of organic chemistry has continued to evolve, with modern advancements revolutionizing our approach to organic synthesis. The Heck reaction, for instance, is a prime example of a novel reaction that has significantly transformed organic synthesis. Named after the American chemist, Richard F. Heck, this reaction allows for the direct formation of carbon-carbon bonds, a crucial process in the creation of complex organic molecules. The reaction has found wide-ranging applications, from the synthesis of pharmaceuticals to the production of polymers. Similarly, metathesis reactions represent another significant stride forward. These reactions, which involve the exchange of parts between two similar compounds, provide a versatile method for the creation of new molecules. The development of catalysts that enable these reactions has unlocked their potential, leading to the Nobel Prize in Chemistry for Robert H. Grubbs, Richard R. Schrock, and Yves Chauvin. Alongside these novel reactions, computational chemistry has emerged as a vital tool. By using sophisticated algorithms and powerful computers, scientists can predict reaction mechanisms and design new molecules in silico before they ever enter a lab. This approach has expedited research, reduced costs, and minimized the use of harmful chemicals. But the evolution of organic chemistry is not only driven by new reactions and digital tools, it's also shaped by societal and environmental needs. In response to the growing concerns about sustainability and environmental impact, the field has seen a surge in the development of green chemistry and sustainable synthesis methods. These approaches seek to minimize waste, reduce energy consumption, and avoid the use of hazardous substances, aligning the practice of chemistry with the goals of a sustainable future. In the light of all these advancements, the future prospects of organic chemistry appear more exciting than ever. With the continuous development of new reactions, computational tools, and sustainable practices, we can expect to see further innovations, more efficient processes, and a broader range of applications. Organic chemistry continues to evolve, shaping our future in response to societal and environmental challenges. But how has all this shaped our understanding of organic molecules and their applications? The impact of organic chemistry discoveries is vast and varied, reaching far beyond the lab and into every corner of our lives. Take pharmaceuticals, for instance. Organic chemistry is the science behind the design and synthesis of drugs, from painkillers to antibiotics, from chemotherapy agents to vaccines. It's this branch of chemistry that has given us the tools to combat diseases and improve human health. In materials science, organic compounds have been fundamental in the development of everything from plastics to high-performance fibers. These materials have transformed industries from construction and transportation to electronics and fashion. Imagine a world without synthetic fabrics or durable plastics. It's hard, isn't it? And let's not forget the role of organic chemistry in agriculture. The development of synthetic fertilizers and pesticides has revolutionized farming, increasing crop yields and making food more abundant and affordable. This is not to mention the crucial role of organic chemistry in biochemistry. It's organic chemistry that helps us understand the complex chemical reactions that take place within living organisms, from DNA replication to energy production. As we reflect on the future prospects of organic chemistry, we can't help but be excited. Emerging technologies are poised to have a significant impact on the field. Artificial intelligence and machine learning are already being used to predict reaction outcomes and design new molecules. Nanotechnology is opening up new possibilities for drug delivery and materials design. And green chemistry is leading the way towards more sustainable and environmentally friendly synthesis methods. These advancements are not only pushing the boundaries of our scientific knowledge but are also addressing some of the most pressing challenges of our time, from climate change to global health crises. As we look ahead, the field of organic chemistry promises to continue its journey of discovery, reshaping our world in ways we can only begin to imagine.